Work Package 2 was tasked with creating 3D point clouds from both laser scan and videogrammetry. Pointivo produced the detailed 3D point clouds with registered imagery for the three bridges using its proprietary videogrammetry algorithms. We reconstructed 4K video that was captured from iPhone 6s. We also captured 2400 high-resolution images for damage and crack detection. These 2400 images were captured across all three bridges, ultimately producing accurate 3D point clouds. The first bridge we captured was in Ackworth, Georgia. It took 63 minutes of capture time. This was captured using three distinct capture paths. You can see paths 1 and 2 on the sides of the bridge. Kept us out of traffic and enabled us to capture the sides of the bridge. To capture underneath the bridge, we had to get out in the middle of the road. This was acceptable for this project, but in future projects or a practical application, it should be noted that this capturing in the middle of the road is dangerous and may require some sort of traffic control or lane stoppages from the Department of Transportation. This is our point cloud for the Ackworth Bridge. It's a 1.5 gigabyte point cloud. It has 21 million points and was processed over 21 days. It's a 140-foot bridge, and point density for this point cloud is approximately 33,000 points per square feet. The second bridge we captured was, we'll call it Gwinnett Bridge 1. We're getting a little better at the capture pattern, so it was only 2 videos to capture this. Also, the span of the bridge was a little bit shorter, so we were able to capture the center of the bridge without actually getting into the road. So you can see from capture paths 1 and 2, it's pretty safe to capture on both sides of the bridge, and we were able to also capture the center or the middle of the underneath the bridge from the safety of the shoulder. This produced a 1.2 gigabyte output. This is a 156-foot bridge. It took 18 days to process and produced a point count of 16 million points for this bridge, with approximately 31,000 points per square feet. The third capture was a bit challenging. This is Gwinnett Bridge 2. We did end up capturing it with one continuous video. So you see here we started on the left side underneath the bridge, and we captured as much on the one side of the bridge as we could without getting into the water. And we actually went up back on top of the bridge and back around to capture that third capture path, which enabled us to capture one continuous video for 65 minutes. This produced a 1.4 gigabyte point cloud. This is a 160-foot bridge. This processing took 20 days and produced a point cloud that had 19 million points with an average point density of approximately 30,000 points per square feet. To start this process, we first had to select the bridge, so we had some criteria to meet in order to reduce the risk for a successful reconstruction. So first we needed a primarily concrete bridge. I think the third bridge had a few steel beams, but we were able to work around that. Ultimately, we were looking for good illumination level, being able to see everything. Photogrammetry relies on illumination, so without good illumination we can't get a good reconstruction. Accessible for video walk under, meaning not over water, which we didn't adhere to, but we were still able to get a successful capture. We're also looking for a short span and a narrow width. This again enabled us to get a good capture without needing to stop traffic or control any traffic or lane stoppages. And lastly, we were looking for a bridge that was under 25 feet. This enabled us to capture from the ground without needing any kind of assistance in seeing underneath the bridge. We did face some capture challenges in this project, one of them being the capture resolution. The scanning resolution and acquisition of the data makes the capture very challenging. Capturing high resolution images is more time consuming than capturing 4K video and takes longer to process. Additionally, capturing the specific bridge components with the high-res images is challenging because the location of these components are difficult or impossible to capture from the ground. To capture the high-resolution images, we took 2,400 images across 3 bridges, but some of these images were focused on general bridge structures and specific bridge elements, and some of those images were focused on potential deterioration components. Another challenge was the capture pattern. Specific capture patterns must be followed to ensure, one, inspector safety, and 2, to minimize the need for traffic control and lane stoppages. Traffic control and lane stoppages could be another challenge. We didn't face it too much in this project except for the first bridge, but even then the traffic was light so we could get out into the road. That being said, that should not be an expectation for bridge inspections to be able to, stop lanes or control traffic. One of the things we looked into for this project was drones to capture the imagery for the bridges. But drones could not be used to capture the necessary data for this project. Specifically, federal laws prevent drone flight within 5 miles of any airport and any flight path above pedestrians and vehicles. So this pretty much eliminates almost all bridges around our area to capture with a drone. Although a drone could provide great overview imagery, it cannot actually provide the detailed imagery that we needed for the purpose of this project. Maybe in the future, high-resolution imagery from drones could be useful in bridge inspections, but these bridges, again, can't be over pedestrians nor near an airport. And all 3 of the bridges for this project were actually in no-fly zones. The imagery was run through our proprietary structure from motion algorithms. We reconstructed the cell phone videos over the course of many days to produce the point clouds. The registration was done on the first 2 point clouds because we had multiple point clouds from the different capture paths. We were able to automatically register these point clouds together based on their geometry. We were very happy with these results. We think they're very comparable to the laser scans, so we were excited to see the outputs. Some important things to note: the laser scans took considerably longer to capture, and they also had many more scans, but the processing time was considerably less with the laser scans. If you notice that the laser scans are approximately 1 to 3 hours for capture time, whereas Pointivo is approximately an hour. It's important to note that these times are still more than bridge inspectors want to spend at the site. However, if the model is created and the inspector only needs to go and capture a little bit of data to update the model, then the Pointivo solution would be a great opportunity to take out your phone, take a video, and update the model that has already been created. One of the most interesting results of this project is the accuracy of the point clouds. When compared to laser scans, our point clouds were less than 1% error, in many cases, less than 0.5% error across the depth length, between the beams and the beam widths. So taken from multiple measurements, we're seeing an average error of less than 1%, which when captured from an iPhone shows very promising results. There are some limitations to the technology. Currently, you can only really use it on concrete bridges because we require texture to successfully reconstruct. Although we did capture a bit of steel on the 3rd bridge, that we are looking for more texture in the scene to ensure a successful reconstruction. The photogrammetry or videogrammetry output was a bit noisy, especially when compared to the laser scan output. So what's required is a more robust algorithm to reduce the noise coming out of the videogrammetry algorithms. Another limitation is the capture and runtime. First off, it's not in real time. And second, as I kind of mentioned before, the inspector is only out on site for about 20 to 30 minutes. So this is too long for them to capture an initial model, but they could update a model that's already been created. And we're not going to get real-time reconstruction. There's too much computational requirements to make that happen. Another limitation to the photogrammetry algorithms is capturing sub-millimeter cracks. It's very time-consuming and requires high-resolution cameras to take enough photos to capture the cracks. The federal mandate in the United States for bridge inspections states that cracks in concrete between 0.15 millimeters and 0.3 millimeters are considered tolerable. Finally, the last limitation is building technical trust with our bridge inspectors. Uh, Data capture still remains very challenging and time-consuming. And ultimately, we need to build trust in the technology, trust in the accuracy, and trust in the operational efficiency of the solution. Thank you.